Hey everyone! Recently, Ian Cuttress of Tech Potato posted a pretty awesome video on interconnects and talked about how that might impact AMD scalability. I'll get to that scalability part in a bit, but first, let's look at some of the speculation about AMD's ring design. At about 18 minutes and 30 seconds in, Ian notes that the core-to-core latency data for Zen 3 and Intel chips look quite different, even when both are using a ring, and questions whether AMD's design is simply a ring or something more. Specifically, he thinks that it might be a bisected ring based on how Zen 3's core-to-core latencies are substantially lower than Intel's. At first glance, if we run a core-to-core latency test that's basically equivalent to Anantech's, or at least Andreas told me so, we can see exactly what Ian is onto. Core-to-core latencies are indeed much higher in Intel's case, even with a shorter ring that only has 4 cores. But taking this data at face value and inferring a difference in interconnects from it is really dangerous because there is a lot more going on than, oh, here's a ring or here's a mesh. The first and probably biggest issue is Intel's separate uncore clock. Intel puts the ring interconnect on a different clock domain than the cores, and in recent Intel architectures like Coffee Lake and Comet Lake, uncore clock is a lot lower than core clock. No doubt Intel is doing this to keep power down. I mean, they said so when they first introduced this design feature in 2013 with Haswell. But for a while, we mostly saw lower uncore clocks in server or high-end desktop chips with longer rings. But with client parts getting higher core counts, longer rings, and higher core clocks, they too were given lower uncore clocks, probably to keep power down. Now, let's look at AMD's side, where the approach is quite different. Here, the L3 cache seems to run the clock speed of the fastest core in the CCX. This seems to be common across all 3 Zen generations. This approach with one clock signal fed to the CCX and coarse grain dividers is certainly not as flexible as Intel's. If we look at a PPR and look at how p-states are defined, we can see that only 1/4 integer divide steps are supported. You also can't run any core in the CCX slower than 1/3 of the fastest core's frequency because of how tightly the L3 and cores are coupled. But taking a step back, there is clearly a discrepancy in clock speeds that we have to address. So here we have an i9 9900K with the uncore clocked to 5 GHz. Just as a reminder, the uncore includes the L3 and ring bus. And just like Zen 3, the 9900K puts 8 cores on a ring. Now, with similar core and ring frequencies, we can see that there's not a whole lot of difference now between the two. Both of these chips pretty much land between 50 and 20 nanoseconds. Intel's values do go a bit higher and a bit lower, so let's address that discrepancy too. So for that, let's look at how one core gets an up-to-date cache line from another, and start with Intel. So first, the core is going to try to fetch the data from its private caches, but in this case, it won't find it there because the cache line has previously been validated when another core needed to write to it. So the next step is to send a lookup request to L3. There, it's going to get an L3 hit in this case because the cache line is in another core, and the L3 cache is inclusive of all private core caches on Intel. Now, the CPU has to make sure you're the only one with the cache line so you can write to it, so it's going to check the core valid bits into L3 to see what other cores have that line cached, and send a message to those cores telling them to invalidate it and possibly write back the data if it's been modified. By the way, that's for Intel CPUs with a ring bus and inclusive L3, so that means everything on the server side up to Broadwell, and everything on the client side up to Ice Lake. Newer chips with a non-inclusive L3 seem to behave a bit differently, and I think for those you'll see an L3 miss in a non-inclusive L3, then a hit in an inclusive probe filter that then tells you which core has it. But anyway, yeah, if you might be looking at this and thinking, all these transfers happen on a ring, right? Well, yeah, the thing is, they don't happen on the same ring. I went through Intel's Uncore performance monitoring documentation and made a pretty rough high-level block diagram of an Intel L3 cache slice. The docs are a bit vague at times, so forgive me if this isn't totally accurate. But I bet you can already see what I'm getting at here. The interconnect isn't as simple as just a ring, so let's look at this ring, or rings, in more detail. If we look at the Uncore performance monitoring docs, Intel's ring bus actually consists of 4 rings. The one we usually hear about is the BL ring, or block ring. That's responsible for moving data and does so 32 bytes at a time. There's also an AD ring, or address ring. That's how you send lookup requests from the cores to L3 cache slices. Then there's an acknowledge ring, or AK ring, that lets agents on the ring bus acknowledge receiving each other's messages. And yes, your messages can bounce on a ring. It's rare, but I suspect that happens when certain queues are full. Finally, there is the IV ring, or invalidate ring. That's how you send snoops, or external lookup requests to other cores, quote, private caches. Basically, you are telling them to kick their private data out because you want to take ownership of it, probably to write to it. And if you're not confused by this yet, get this. Not all of these rings are created equal. Of those 4 rings, 3 of them are bidirectional. So the BL, AD, and AK rings are bidirectional, meaning that each of those actually consists of 2 rings, a clockwise ring and a counterclockwise ring. The IV ring, however, is unidirectional, and there is only 1 IV ring. Now, you might be thinking, why didn't they make that bidirectional as well? Well, if you look at how often these rings are utilized, so say you are an L3 cache slice looking at the ring bus going by, and utilization is how often are you seeing a message pass by in terms of cycles, like cycles you see a message pass by divided by total on-core clocks. You're going to see that the IV ring is a lot less heavily utilized than other rings. So it doesn't really make sense to throw die area and power at running more wires around to make this IV ring bidirectional. So now we have a more complete picture of what's going on for Intel. We are traversing a bidirectional ring a couple times, but in the process we also need to traverse a unidirectional ring. So here is a core-to-core latency diagram for a Haswell chip, just to make things easier to see because there are only 4 cores. You can see that the first core seems to be farthest away from the cache slice that is handling the test data. I'm guessing it's simply at the wrong end of the IV ring, which is unidirectional, and that would explain some of the larger discrepancies we see in Intel's test results. Basically, the explanation is one of these rings is not bidirectional. Now, what about AMD? It turns out they do things differently, and fortunately they do outline a process in their optimization manual. It's the same for all Zen generations. Basically, Zen keeps duplicate copies of the L2 tag array that AMD calls shadow tags. If there's an L3 miss, it searches those shadow tags to see whether another core in the CCX has it in its private caches. To make that work, Zen 2's L2 cache is inclusive of its L1 cache, so only the L2 tags have to be checked. If that shadow tag search comes up empty, well then the CCX is going to send a request out to the Infinity Fabric, but in this case it won't come up empty. We know the data is in another core in the CCX. Now we have a better picture of the core-to-core flow for both AMD and Intel. As you can see, things are very different after the L3 lookup. On Intel, you traverse a unidirectional ring. I don't know what interconnect AMD uses for the shadow tags, although Wikiship does say the shadow tags duplicate the L2 state and tag entries for indexes in that slice, so maybe it doesn't need another hop on the interconnect. Maybe it's checked right there in the L3 cache slice, and that L3 cache slice manages the entire lifecycle of a request to L3, regardless of whether it's a hit or miss. And afterwards, it's not totally clear what happens either. AMD definitely needs to invalidate the cache line from the core that had it before it can now allow another core to write to it. But I'm not totally sure how that message gets passed around. My guess is it's also passed around on a bidirectional ring, and that would eliminate the core at the wrong end of a ring kind of pattern we see with Intel. Anyway, it's clear that taking core-to-core test results and comparing the two is a lot more complicated than first meets the eye. And in my opinion, the results don't suggest a bisected ring for AMD. There are far better explanations like differences in ring clock or Intel's unidirectional invalidate ring. Remember when I said I was going to get back to scalability? Yep, here we are. Ian talks about how extending a ring to serve 12 or 16 cores might be pushing things, and I generally agree. You see, as you extend a ring and add more stops, you're going to increase latency, but there are other ways to use one ring to serve more cores. You see, one ring stop doesn't have to correspond to one core. For example, Qualcomm in their Centriq server CPU makes 2 cores share a single ring stop. That keeps the number of ring stops down, which keeps latency in check, and lets a single ring segment handle 24 cores with 12 ring stops. For an example of a client platform doing this, Intel's recently announced Alder Lake architecture does something similar. It has 16 total cores, but only 10 ring stops for those cores. 4 little Grayspawn cores share a single ring stop. Now you might be thinking, hey, with that many cores sharing a ring stop, won't they see contention for ring access? Well, as always, there is more than one solution to the problem. You see, you can either have more ring stops to let more traffic onto the ring, or you can reduce the bandwidth that you need from the ring in the first place. And Intel does this by putting a very large 4 megabyte L2 between those 4 Grayspawn cores and the ring. For a practical example, Sandy Bridge has a 256 kilobyte L2 cache and sees about 12 L2 misses per 1,000 instructions, or MPKI for short. That's when running Cinebench R15 in multi-threaded mode. PyDriver, in contrast, has a much larger 2 megabyte L2 and sees just above 2 L2 cache misses per 1,000 instructions. That's more than a 5x reduction in L2 misses per instruction, which means a lot less traffic to whatever is beyond L2. So Intel's 4 megabyte cache reduced the miss rate even further, and that means that this cluster of 4 fairly powerful cores can do just fine with one ring stop. AMD could easily do the same thing. If they have enough L2 to reduce demands on L3 and memory bandwidth, 2 cores could share a single ring stop. That will let AMD scale a CCX's 16 cores without using a larger ring, which keeps L3 latency down. Now, back to Ian's video. About 19 minutes and 12 seconds in, he says, so the question here is, where does AMD go from this? And then talks about options for scaling up core count, like using a mesh. Of course, I can't predict the future, so let's look at what AMD has said so far. As we've heard quite a few times already, chiplets are all about reducing cost. That cost is not going down, so I think it makes sense for AMD to stick to the strategy of using lots of small chiplets rather than bigger ones with more cores per chiplet. From the Gigabyte data breach, we already see this strategy in action with Genoa, or Zen 4 in a server config. AMD is going to use 12 CCDs, numbered from 0 to 11, to increase core count, and stays at 8 cores per CCD. They can probably use the same strategy for client too. There is enough room on the AM4 package, for example, to use 3 CCDs in order to increase core count. You would have to move to IO die, but it all fits, and that would get you to 24 cores in a client platform. Okay, that's going to wrap it up for now. Thanks for watching, and props to Ian for making his video, which I'm going to link in the description below. I really like seeing this kind of analysis from tech media, and I would love to see more along those lines.